bro.
Jam to streamirovat, mě to pegá. Let's go. All right. Welcome. To me trying to learn some assembly for, yeah, I don't know. I did some x86 in university and forgot 90% of it. And I don't want to do x86. I don't want to do ARM. I just want to do something primitive. So 6502 is apparently the thing, the processor used, the microprocessor used in the Apple II and some other devices. So I wanna check it out. Okay, cool. Found this great tutorial, by the way. Has an emulator too, so makes sense. Probably would be nice to create something at the same time. In my, yeah, that's my product. So assembly, let's go there. Okay, cool. Keep it for later. So it's a tiny ebook. Okay. I need a mouse. I hate the trackpad. Ah, crap. Give me a sec. Right. Okay, got my mouse with no battery. Let's see if I can charge and use it. I think that's possible. Not this. Okay. Okay. So let's start. Probably need to keep some notes. So I'll keep some notes. Font's tiny. It's called EZ6502 source. Should use NeoVim. Okay. Intro. All right, let's start. We have. Should I do the stupid? Not stupid, but the Primogen style of reading. Okay, I'll read everything out loud. Probably help me read because I like skipping over stuff. So I'm a very bad reader. So this will force some discipline. Okay, so in this tiny ebook, I'm going to show you how to get started with writing 6502 assembly language. 6502 processor was made in the 70s and 80s, powering famous computers like the BBC Micro, whatever that is, Apple II, okay, and NES. Bender in Futurama has a 6502 processor for brain. Even the Terminator was programmed. Okay, cool. So why would you want to learn 6502? It's a dead language, isn't it? Well, so is Latin. They still teach that. QED. Quod eros demonstratum. Actually, I've been reliably informed that 6502 are still being produced by Western design center and solo hobbyists. Okay, barely, not dead. Seriously though, I think it's valuable to have an understanding of assembly language. Assembly language is the lowest level of abstraction in computers. Yeah, well, almost. Okay, the point at which the code is still readable. True. Assembly language translates directly to the bytes that are executed by your computer's processor. If you understand how it works, you basically become a computer magician. Magic and software development. Nice. Anything you don't understand? That's a nice one. Dave technique. Okay, so there are two techniques. One is you record onto tape. So you have to learn how tape machine worked. To learn how tape machine worked, you understand some hysterics, remnants, modulation, blah blah. We also understand how radio worked. So we learned about amplitude, humanization of stereo FM, blah 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 blah, DC, blah 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 blah. Pretty deep, nice. Did that knowledge make me a better recording engineer? Probably not. But it was helpful basis. And then the other one is start with N node ALU, CPU, MIDI. Abstraction. Joel has a lot of cool things to say, and I think I read this once. All abstractions are leaky. We can rely on Schiller on the levels below our current level. Right, so you kind of always leaks down. Okay. Back to TCP. Earlier, for the sake of simplicity, I told a little fib, but some of you have steam coming out of your ears because this fib is driving you crazy. I said that TCP guarantees that your message will arrive. It doesn't actually. If your pet snake has chewed through your network cable leading to your computer and no IP packets can get through, then TCP can't do anything about it and your message doesn't arrive. If you were curt with the system administrators in your company and they punished you by plugging you into an overloaded hub, only some of your IP packets will get through. And TCP will work, but everything will be really slow. This is what I call a leaky abstraction. TCP attempts to provide a complete abstraction of an underlying unreliable network, but sometimes the network leaks through the abstraction and you feel the things the abstraction can't protect you from. Abstractions fail, sometimes a little, sometimes a lot, there's leakage. Okay, some other examples. Something as simple as iterating over a large two-dimensional array can have radically different performance if you do it horizontally rather than vertically, depending on the grain of the wood. One direction may result in vastly more page faults than the other direction, and page faults are slow. Even assembly programmers are supposed to be allowed to pretend that they have a big flat address space, but a virtual memory means it's really just an abstraction which leaks when there's a page fault. Okay, I guess, what are they really saying? What was the page fault? Oh yeah, it's that basically virtual, the way virtual memory works, you split your virtual memory into these things called pages. So there's just a bunch of blocks. And the thing is, not all of it is in actual physical memory at the same time. So obviously you can't, because if you have, when you virtualize memory, you kind of, you let every application think they have like, I don't know, let's say 8 gigs available, but they don't, because if you have 100 programs running, you don't have 800 gigs of RAM. And so some stuff is not in memory, and then you have a page fault when it's not in memory. Right, that's what a page fault is. No, not that. What's page fault? The exception that the MMU raises when a process accesses the memory page without proper preparations. What is that? The page requires a mapping. Besides the actual main, okay, yeah, the actual page contents may need to be loaded for a backing source such as a disk. The MMU detects the page fault, but the operating system kernel. Okay. If the page is loaded. Yeah, if the page is loaded in memory at the time the fault is generated but is not marked, then it's called a minor or soft page fault. Okay, and the major one is delays. The system delays loading parts of the program from disk until the program attempts to use it and the page fault is generated. If the page fault is not loaded in memory at the time of fault, yeah, so that's one. And you have, it's just an exception, technically it's a category, so sometimes it's probably, I guess the way I get it is that it's planned sometimes. I was also currently reading not this, where's the oh no, didn't have it here. Okay, 3 Easy Pieces. I don't know if it's copyright protected or so. Yeah, it's free here, so what I say, sorry, just gonna read a part. We got, yeah, dialogue on memory management, that's cool, but the dialogue, yeah, okay, let's go here. All right, yeah, we started with 6502 and now we're gonna go into paging. This is what often happens to me. It's also good to have it on video to see how I lose time or how I waste time. How to virtualize memory without segment. How can we virtualize memory in a way as to avoid give me a sec, I just gotta send this message. Okay. Okay, so you do a segmentation, managing free space. Okay, so managing the segmentation, that's so nice. Paging. Okay. Instead of splitting of order into 3 logical segments, called page. Da-da-da. Okay, okay, tab, gonna use a tiny address space with 16 byte pages. In this case with 4 pages only. And then in physical memory, right, you put some, yeah, as you can see. I guess what I want to see now is the page fault. That's okay. Is there an index somewhere? Can search. Ah, okay. We mentioned the MMU. Yeah, this is actually very interesting to read about. The way it works is pretty clever. But I'm kind of trying to see the return from trap when they are unmapped. I don't see the word page fault anywhere. Because I wanted to see if it's desired, if the page fault is if it's like you kind of allow it in some cases. Page fault. Oh, okay, cool. The page fault. Recall that the TLP we have two types of systems: hardware managed TLPs, software managed. In either case, the page was put in charge to handle page fault. Okay, so it's all software handled. If it's not, when you just publish it, just started the page fault. Okay, yeah, but so I guess there are valid reasons why it'll happen. So, okay, cool. Anyway, leaky abstractions. So that's what he was saying with leaky abstractions, and then basically you always have this. Whatever you're abstracting, it's always okay. Now I get it. Whenever you write any kind of abstraction, what is an abstraction? It's essentially your okay. I'll try to draw it the way I see it in my head. Okay, so let's say your true. I need to disable my goddamn stupid plugin. Disable for once. No, whatever. So let's say your kind of program has this kind of fine-grained detail, whatever you have, and maybe they are kind of organized in bigger units. Something like this, whatever. And let's say that your abstraction, what it kind of does is it sort of gives you two parts. So that's one, and that's, let's say, two, for whatever reason. I want the subcomponents, so except for this big green thing, I want these subcomponents to have kind of a fill. Can I have a fill, please? No, that'll mess up the colors. Okay. Right, whatever they are. And what your abstraction gives you is these two. So it's sort of, now this is bad, and what I'm doing is like grouping. It's not really just grouping, it's more like, no, I found something better. Okay, found something better. Let's say you have some interesting shapes. Okay. So let's say you kind of have a system like, all right, so what your abstraction does, converts this to these things. Okay, you get, for that you get a rectangle, you get a circle, you get a triangle, which is funny. Can't draw it, I think, here. Can I draw a straight shape? Ah, no, can't. Really? Okay, I'm gonna pretend this is straight. Okay, so you're treating these shapes as this, and now in most of the cases when you use, oh crap, yeah, great. This is why you don't keep kitchen utensils on your desk, because now something's dirty. Yeah, whatever. Screw it. Anyway, so you get this. This looks pretty okay, because you can treat this as a rectangle in most cases. But then when something breaks down in the detail, when it's very important what the shape of this object, it's very important that this angle, in some particular calculation, it's very important that you have this, for whatever reason, then of course this abstraction won't do, so it'll leak. That's what Joel means by leaky. It means that this assumption you sort of have somewhere, it'll leak, and then to understand why something's failing, you need to go down here. So that's the leak. Okay, I think that's the only way I can put it. Probably delete this. Okay, so that's the way he means it, and he uses some other examples. Yeah, whatever. C++ string classes. Oh, here's a real life example. You can't drive as fast when it's raining. By the way, does my audio even work? Let me check. I think that's the only way I can put it. It does work, great. Just double checking. Okay, and you can't drive as fast as when it's raining, even though your car has windshield wipers and headlights and a roof and a heater. All of which protect you from caring about the fact that it's raining. They abstract away the weather, but low, you have to worry about hydroplaning or aquaplaning in England. And sometimes the rain is so strong you can't see very far ahead, so you go slower in the rain because the weather can never be completely abstracted away because of the law of the abstractions. Okay, yeah. So of course, basically abstractions serve probably to cover 95% of cases that really appear in the wild, or just sort of give you a really nice way to deal with the most useful cases, even most cases maybe, but every now and then you get a crazy case and destroys everything. The worst is when you have a naive system designer who only looks at probabilities and not outcomes. So basically, if you have a power law distribution where let's say like Pareto, where 20% of events are responsible for 80% of some effect, you can imagine that if you make an abstraction that deals perfectly well with 80% of the cases, and exactly that 80% of the cases that are not these 20 crucial percent, your abstraction is effectively useless because it helps you deal with the least significant parts. And by dealing with the least significant parts, even though you have technically covered most of the cases, you covered the least useful cases. Sometimes probably would have made more sense to only abstract away the 20 important percent, whatever. But the point is that whenever you have an abstraction, you kind of need to look at the impact. So you need to cover the cases with most impact, not just the ones that appear more often. So, I mean, sometimes and often a metric in computer science is that the cases that appear most often are also the ones with the most impact by virtue of appearing often, because the impact might be time saved. So, for example, if for a developer, let's say you create an abstraction that the program has to deal with 90% of the time, like numbers, let's say, right? Integers. So if you don't have an abstraction for an integer and use something, I don't know, crazy, then yeah. The reason that integers have an outsized impact or a lot of impact is because they are used so often, because the thing you're abstracting for is improving developer productivity. often when you design something like that, you want to improve developer productivity. It's not really just performance. You have these other concerns. So something like that. Anyway, let me just respond. Okay. So what I want to say. Yeah, basically that's it. And so I'm gonna skip now. Although these are all cool things to know. I'm gonna go away. So anyway, cool. Whatever. Repeated something important. Look at that detour, that rabbit hole. Okay. So it is the lure and you become a magician. That's why 6502. Why not a useful assembly language x86? Great, he's gonna explain exactly why I chose this blog post. I hate x86, but let's see if he has the same reasons. So okay, I don't think learning x86 is useful. Okay, interesting. I don't think you'll ever have to write assembly language in your day job. This is purely an academic exercise, something to expand your mind and thinking. And then, yeah, because it's simpler, you learn more. Cool. Okay, is it designed to be written by humans? More modern assembly languages are meant to be written by compilers, so let's leave it to them. Buzz 6502 is fun. Nobody ever called x86 fun. Yeah, exactly. I mean, I hope 6502 is fun, but yeah, this one. Okay, so this guy also wrote an assembler, which is cool. Sorry, I'm not just an assembler, a simulator or emulator, whatever, for this microprocessor, for this assembly language. Okay, so if I run this, it paints 3 pixels here. If I'm probably reset and I go, oh no, let's go sort of step by step maybe. Debugger mode step. Okay, what I don't like is, okay, so this is nice because it does give you the memory. But I don't like that it doesn't give me the what's this? I don't like that it doesn't give me the steps. Like I don't have like a pointer here where I'm at. Okay, but I assume first step is loading that, then second step, that's the probably this address is something. The 0th pixel, the first pixel, the second pixel. Probably these are just colors. So if I just change that, okay, I will assemble. I will reset. I will debug. Oh yeah, interesting. Yeah. And these are just the pixels. So technically, if I just repeat this, I'm going to repeat it, but I'm going to use this. So let me kind of do it like that. There's got to be a way. Now, first of all, let's change the colors. Now there's got to be a way for me to paste with, how do I increment these now? I mean, I know that technically I can do something like, technically I can do something like this in Vim. So I can update by 3, but this is slow. Okay, I have an idea. I'm going to write a little Python script to do that. So, okay, so I'm going to add a generate. Okay, from random import rand int. Does that work? 0 to 10 is nice. Okay, so let's do 430 for 100 pixels, I guess. For I in range 100, I will go color is rand int 110. LDA hash dollar. Print LDR hash dollar 0. Can I do an F string? Does that work? Let's try that. Okay, it does. But it generates a 10, which I didn't want. Okay. Nine. Print that. And then STA in 0, 0, 0. Okay, just count up from 200. So count is just 200 plus I. And then I go print F. It's just $0 and then the number dollar. Oh wait, STA $0, then the number count. Dang. Okay. Oh, this is taking quite a long time. Is there a bug? Do I have a bug? Let's check. Okay, something obviously not working here. Syntax error. Okay, in the beginning already a syntax error. Oh, LDA, STA. Oh, LDA, not idiot. Okay, let's copy this. Go here. LDA, LDR, LDA. Okay. Just read their message, man. That's pretty cool. But why the 2 blocks? Because I only, or do I generate zeros somewhere? Is that no? That's too convenient. I want to know where. Ooh, so if I cut around here in half, what happens then? Okay, that is indeed in the. Do I have any 0, 0 somewhere? Maybe the 0, 0 is a black color. I don't see any 0, 0s because I think my. Let me check. Yeah, that's the only 0, 0. So something is happening here that's just jumping. Okay, so if I just repeat that. Wait, what the hell is happening? So that stops with this many pixels. Big question is, why does running it multiple times? No, it doesn't change anything. Okay. Okay, let's. again the same? Of course it's the same, it's idiot. 18, so let's go for 20 lines. Let's see what 20 lines do. That's how far it goes. And if I go for 40 lines, so interesting, at around half. Are these octal? Is that the thing? These no. Well, oh no, octal would make sense. Alright, so I'll go, that starts at 0, 0, so 09 is the last one, then I need to stop here. Okay. That's the half. 1, 2, 3, 4, 5, 6, 7, 8. That's 10 of them. And then the other 10 skip. What? Maybe it's hex. Okay, it's probably hex because the exact gap. Yeah, it's hex, it's hex. So if I went and I said A, oh, this is gonna be fun. Ooh, 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 ooh. So I went 0B and then 0C and then D. Ah, haha, got it. Okay. So if I go back to Python, it's also stupid that I do this and not kind of copy it. 26. Okay. Great Vim skills. Okay, let's create a intro py file, paste this, import randint, okay, and I need this in, wait, how does hex get used? You give it a number, it gives you a hex, but I want it without the, so it's not, yeah, I want it like this. It's not a multiple of 4. Okay, now it is. So I'm going to run this and I'm gonna clip it, copy its output, if that works. Not LDR, sorry. Oops. A. Let's run that command. Okay. Is it too much to draw, or what's the problem? It should be capital. So what is it from? No, I think it's a string dot upper. That's the function. Let's see if that works. Also not. That's because certainly this is wrong. It's saying 0C8. No, it's my mistake. So the 2 there needs to be a plus 2 times 16 times 0 plus I. Yeah, that's correct. Something like that. Yep. Okay. Very, very nice. So how many intros did I do? I did 100 and I had 4 left over. So 96 over 3, that's 32. Well, probably makes sense. So I'll do 32 by 32, is that right? It looks like a 32 by 32 box. So let's do. Haha! Well, that's an amazing result, I have to say. And as far as the colors go, I'm curious how many bit colors does it have? Okay, let's try 32 bits, just sort of out of sheer curiosity. So I'm going to generate something between 0 and 31. I'm going to hex to this dot upper. The big question is, no, I don't like. Oh, this is gonna be tough. I don't know if that's gonna work. I think it needs a 0. Well, but it works. Does it? Does it have all the colors? No, I mean, it doesn't have this, right? There is a Python 2 digits. So how do I force it? Yeah. Okay, so it's so you give it a format and you say 0 to x. Cool. So you call the format. It's a randint between 0 and 31. The format is 0 to x, and then operate. I guess that's what I'm thinking, because I want to see a true. I guess that's a true. Because well, let's try going over the boundary. So if I do ff, it is a color, but if I go with 3, yeah, there is a syntax error, because okay, now let's run. Let's go to the hex dump. Okay, so we will now see the whole thing from 0 to 100. Does it have a 0 to 100? Okay, starting at, yeah, it does. Oh, no, it doesn't. It starts there. Disassemble. Okay, these are the instructions, but it doesn't, the hex dump doesn't have the memory of that part. I don't see it, at least. Let's see if by any chance I have 1918 anywhere, or 0809, or 0908, or 0818. No. Okay, so it's not here. Yeah, probably this is going to answer it later. Okay, so let's read. Yeah, it's gonna have that. So ours has more pixels, and then, okay, let's sort of let it debug. So one step. It's say let's reset. Okay, it's saying it changed to 01. That's because of course, in our case, it'll change to 18, which is a hex. And PC changed from 600 to 602 because every instruction is 2 bytes. 2 bytes, I guess. Yeah. Yeah. Rather, sorry, that would be right. Let me check. That's 16. Byte, 4, 5, 6, 7, 8, and then another 8 bytes. So an instruction, there's 2 bytes, so that's the instruction LDA, and then how long is the other instruction? It just jumps to, okay, it's 3, but it's 3. So if you see, this means A9 load 18, as you can see, and then this means STA 0002. It's storing them in reverse order. This is what is it called? The little endian or big endian? I always forget. Does this remember? Basically, it's not storing in the way you see them. So it's storing the little end first. Like just little endian. Okay, endian is. It is little endian. Little endian. Okay. That's cool. Yeah, I kind of remembered a few things. Okay, so let's just now look at this correspondence. Okay, we have load 18. This is load into A18. Then this is S store into A. This number, so little endian first, and then again store 19 load 0201. Yeah. Okay. That's pretty nice. So I'm actually going to do something cool. I will screenshot these few commands and go to ExcaliDraw and then get this part as well. Okay. All right, so I will now okay, first of all, gotta fix this. No fill, red, normal stroke, no sloppiness. Okay, so we gonna be thicker than that. So we will go. Now let's draw the other box. Probably let's go with this. So 5, that's this. And then of course this, come on now. And then this part is, let's draw it again. So if I can conclude, each opcode is 1 byte, 8-bit. Can just put it here. Yeah. Sort of really annoying place to draw this. Let's go somewhere else and let's get this nonsense. Whatever, here, yeah. Anyway, don't care about that right now. Okay, so now we've established something. The other thing, probably cool to also establish, is that sort of let's kind of go here that's a bad idea. I would like to go. Wait a second. Let me do that. And then, yeah, this is the cool part. Little endian stored as 0002. Okay, so that's the cool part, and then the rest, of course, we can follow. I would like this as a thing to export, save in exactly the folder I want it to be in. LDA SDA xdump png, and then in my tutorial write each opcode is 8-bit 1 byte. It's a little endian architecture. For example, LDA is appears in the xdump as, what was it again, A918, as A918, with A9 being the opcode for LDA. Recall that means hexadecimal. Actually, 18 is, in this case, 24 in decimal. Okay. Then a D, sorry, what is the command? SDA 0200 appears as H8, and then we have 8D0002, DA, 8D being the opcode for STA and 0002. How has it 00 is stored? Okay, cool. Now we have that. C figure. LDA, SDA, hexdump, PNG, something like that. I don't have mocked preview. Anyway, doesn't matter. So this stuff I can kind of delete for now. Okay. So we learned something basic. Let's remove my filter. Okay, we learned something basic, which is cool. So now, okay, let's change this. Any number, yeah. Oh, that's the 8. So how many registers? Let's just sort of Google what 60902 even sort of has for a setup. Okay, technical description. It has one. Oh, it's very simple. It's very, very simple. It has an accumulator, the A register, the main thing. It has an X and Y index register. It has a stack pointer. These are all 8-bit, and it has a 16-bit program counter. And it has program counter is 16-bit, 2 bytes, hence a So we got that done. Now the X and Y registers, they don't move as I saw, do they? In this case they don't, because there's nothing there. Okay, so whatever. What is the end? What do these index registers do? Okay, so this is for just useful for stepping through strings and arrays, loop iterations, stuff like that. Okay, cool. Try changing the color. Change one of the pixels at the bottom right corner, which is 5FF, which is exactly, by the way, if you check out my program here, aha, I did it. Okay. SP is a stack pointer. PC is the program. By the way, let me read the notes before I do anything. Memory location FE contains a random. Oh. Oh. So technically, this is gonna be fun. How do I access? How do I do it? Can I do this? Oh, whoa. Wait. What if I do? Sorry, was it FE or I forgot? FE. Okay. FE. That's pretty cool. Is it, play up. Opposite thing. I don't want that. I wanted no. Keep it FE, but dollar. Okay. Now let's go. Boom. Oh. Ha. Def random color generator, but internal, I guess, yeah, internal random color generator. Guess if I go FE, the FE register has a random value on each run, byte on each run. By the way, note that FE are different. Also the register in memory look. Yeah, is it a register? Did it say register? Or is it? No, not the FE mem location. The memory location at FE has a random byte on every after each step. Therefore, it can be used to generate random colors. For the example above, note, however, that there is a difference between FE, which loads the value FE, versus FE into A versus LDA FE, which loads the memory contents of location FE with address FE into A. Okay, that's very it's very important. I learned just by doing it. Probably is going to mention it. The last section shows the processor flags. Okay, that's a bunch of flags. If there's an overflow, break. Okay, we'll check that later. Probably can help with a bunch of stuff. Get some water. So the LDA tags to X. What is X? Oh, the X register increment at C. Okay. So let's go to enable. Right now it's got C0, as you can see. Then if you can see it's 0, 0. After this there will be C0, there will be C1, and then it's going to add the hex value to so that's going to C0 and C4 to the error. So is there gonna be an overflow? Yeah, because CNC of course will exceed the limit. So 84 instead of 184. But this processor, what's up with that? It's too big. If you look at you have the carry flag. Oh, so if you actually look here, it is set. Nice, very nice. Okay. Well, let's look at the tax instruction. It's yeah, mostly it's just one byte. Cool. Break, we're done. So learn about that. Similar load type, don't paste the following code. Okay. So AT STA01 EC0. Okay, let's predict what will happen. So you load this value here. You STA it in memory location 01, and then you add this value, so it should be 81. So that'll be 80, and that'll have whatever some value, and then it'll be 81. Wait. Add the ADC does what? It adds that value. Ooh, sorry. It adds it to itself. Ha, because it's adding the memory location. Okay, now we're going to do this. We're gonna reset it. I'm gonna step, and I'm gonna look at the hex dump. Now it only gives me that. This never gives me memory, which I hate. Okay, what is the... Oh, okay. Oh, this shows the whole memory. So step 1, so now we have 80. So if you add 80 to 80, look at the carry bit. 8 and 8 will be 16, which is more. This should be 100. We can double check this, by the way, in Python. If you just C and then you go 0x80 plus 0x80. That didn't work. I guess I have to print it. 256, and I want to hex it again. Yeah, so that's why you see for this and look at that thing, but a bunch of shit changes. Look at it again. Wait. If I start, okay, what are these flags? Let's look at the flags. N flag says negative. I don't get. Oh, it says negative because it's an 8 means the bell's ringing. Give me a second. Okay. So the negative, I'm assuming that's because this is here like two's complement form, which would mean that, wait, what would it look like if it's in bits? So oh, it's a byte. 80 is a byte, and that's what it is a value. It's no, it's not the high. Of course, the highest bit is not set. Oh no! Wait! No, wait. Oh, it is because that's now 0, 1, 2. No, so that's 1, 2, 4. Yeah. Okay. So look at this. Subtle detail. Very subtle detail. An 80. 80. Okay. 080 is 0B. 100 000. Okay. That's negative. If you think about it in 2's complement form, this is the highest negative number. That's where you get the negative bit set. So I'm going to remove this. That's why you have the negative bit set. So you go 1, that's the negative bit. That's the only bit that gets that. Then you store it, and then a bunch of bit change. This changes, and this changes, and the 0 as well. Oh, the 0 gets set too. So you get the 0 set, you get the overflow set, of course. And why do you get 0 set? Because the value becomes 0, I guess. Yeah. Okay. Cool. Yeah. So it's gonna. Let's see if I guessed it. All right. So the exercises. Text. So that program that used. We can try this. Boom, boom. Probably does the same thing more or less. And this is gonna be funny. Okay, so SDC, or no, SBC, add and subtract with carry. This is very funny. You would expect there's nothing there you would expect. Here's the big question. Why is it FF? FF, if you use to complement form, means -1. I mean, I would have expected 0, of course. So maybe let's do this. It says 7e, which makes sense. Or does it? What does 7e look like? I can just go to Python here and 6 bin, yeah, so why 7e? Well, there's a carry. So I guess because if you look at, okay. Let's think of it as right, 2 to the 7. Yeah, so think of it minus that, -1. But that's too big. Is there an overflow? V is for overflow. So it can't handle that, so it'll trim it. Seven, so not 8. That's 127, which can be represented by by all ones. Except in this case, this is saying that's a 0. I guess if I write it down somewhere, so if I look here and I go, what I have as a number first, I have 80, so we have this, and I want to minus it with of course to subtract this, it's a 0, but it's taking from this. this is 0 is taking from this, which should take 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 from... does it? What I'm trying to get at is if I have, let's say, normal numbers and I go I don't know basic algorithms, and that's 0. Oh, yeah, well, that makes sense. Interesting. Why do I get different results? Yeah, so that's correct. Why I get that is explainable. And now, probably if I choose a different number. Yeah. It's not 3fi, I don't know why it's doing that. Oder ich glaube, ich liege falsch. Kann nicht sein, dass 0 plus 1 ist 1. Nee. Tatsächlich. Ja, what the fuck is that thing down? Yeah, I'll have to check that. Okay, enough for today. I'm tired. But this was good. I need to continue this. It goes to this, creates a game. So it's a nice mini exercise. Okay, I'll check it out.